In this lesson, we are going to explore questions that surround complex roots of unity. So sometimes those questions will actually use the wording roots of unity, and sometimes those questions have specific notation or specific values used in them that let us know we can apply this property. So firstly, what are complex roots of unity? Well, we know that unit means one. So that means that we are exploring any equation where the solutions of that equation are equal to 1. We've also seen before that unity brings into play lots of other geometrical applications, particularly those around the unit circle. So just for a little bit of a recap, we know that every single radian line from the center of our circle here out to the circumference is going to have a value, a radius value of 1, because we're working with the unit circle. So it doesn't matter where I take that radius length, all of those radius length values will be equal to 1. And I can also see that as I move my way around that circle, turning that radius length, I produce lots of nice exact values for radian measures that we know. So 30, 45, 60 degrees, 90, 180, 270, all of those exact values are produced really nicely on our unit circle. Let's look at this in the context of an example that we know and we've solved before, really early on in our complex numbers topic. So here we're being asked to solve the equation z cubed is equal to 1. So this is a nice example of a complex roots of unity equation with a degree of 3, knowing that we should be able to obtain 3 roots, and knowing that the first one is going to be a real root of 1, and that the second and third roots will be conjugates of each other, given that my coefficient of z cubed is a real number. So we've seen quite a few times now that we want to use polynomial techniques to be able to find the roots of this polynomial, and in this case, this one factorizes really nicely because we have been given the difference of 2 cubes. So looking at the solutions from this factorization, we see that we obtain our first root here of 1, and then our second 2 roots in conjugate pairs come from solving the quadratic equation on this second factor that we obtain when we factorize the cubic. So if we plot these roots on our Argand diagram, we can see quite a few properties take shape that will always hold true for complex roots of unity. The first property is that the number of roots will always match the degree of z. So we just solved for z cubed and we obtained 3 roots. Z to the power of 4 will have 4, z to the power of 5 will have 5, so z to the power of n will have n number of roots. The second is that the modulus of z is equal to 1 for all roots. So remembering that the modulus is measuring the length from the origin out to that complex value, which we can see on that first root, given that moving from the origin to the point 1 on the x-axis gives us a length of 1, but this will hold true for all of the roots that are generated from the origin out to their position on the Argand diagram. The third property is that the roots will always equally space themselves around the Argand diagram, and we can see this in red here, where the distance between each of my roots appears to be about the same degrees. In fact, the roots are actually splitting the entire circle into 3 equal sections. So each of these roots is therefore a rotation of 2 pi divided by 3 radians. The last property is that the roots will always form the vertices of a regular polygon. So we can see here when I draw in these yellow lines that look identical in length to each other and can be proven using congruent triangles that they are identical in length to each other, that we end up with an equilateral triangle where the three roots we found are the vertices of that triangle. If we were going to plot the four roots for z to the power of 4 is equal to 1, we would end up with a square, and so on, with each set of our roots creating that regular polygon with equal sides, equally spaced around the Argand diagram. So it would be a good idea to pause this video here and write this summary down in your books. And then we're going to have a look at what this looks like when we convert this into polar and exponential form, which is often easier to work with than the rectangular or Cartesian form that we're currently working with. So let's now explore these roots in polar and exponential form, and knowing that the process to convert to either polar form or exponential form is basically the same. It requires us to find the modulus and the argument of our complex number and then rewrite it in that format. Now, often questions involving roots of unity will, instead of using the variable z to denote a complex number, they'll use the variable omega, which lets us know notation-wise that we are working with z is equal to 1 as our first root, even if they don't explicitly say that. So let's see how we can rewrite this equation in polar and exponential form, specifically rewriting this value of 1 on the right hand side in polar form or in exponential form to enable us to work in that scenario instead. So let's consider the roots of omega cubed being equal to 1 in polar form. So we know that we need a modulus of omega, which is the length from the origin out to the point, or the complex number on the Argand diagram. And we can see that that distance, that length we spoke about earlier, is equal to 1. So we've got that R value that needs to sit out the front of our cos and I sine values. And then we need our argument value. And we know our argument is the angle of inclination from that positive x-axis. But if we have a look at Z1 here, the angle of inclination is 0. The root itself is lying on the x-axis. So that gives me an initial or principal argument of 0, being the smallest angle that is possible to generate that first root of 1. But we also know that we can add full rotations of that unit circle to that root infinite number of times and keep generating that root of positive 1 back as well. So while 0 will be the principal argument or the smallest possible value of theta, I could also use 2 pi as my value and it will give me back the first root of 1. I could use 4 pi, 6 pi, and so on. And each of these is going to give me back that value of positive 1 on the right-hand side of my equation. Now we also know that we can use this modulus and argument to rewrite these answers in exponential form as well. So using that exponential form, each of these are also valid answers for that value of 1 on the right-hand side. So now I've rewritten my equation in polar and in exponential form, but what I really needed to do was solve this equation for not omega cubed, but omega itself. And so to do that, I need to look to take a power of a third on both sides of the equation. So this means that I'm looking to put each of these solutions to the power of a third, in whatever form I've written it in, whether it's polar or whether it's exponential. So in polar form, or modulus argument form, we know that as we take powers of those numbers, it brings into play de Moivre's theorem, which says that I can divide each of my arguments here by 3. So 0 divided by 3 is still going to give me 0, but 2 pi divided by 3 is 2 pi on 3, and 4 pi on 3 is just outside our normal domain. So we would be looking to list that 4 pi on 3 instead as the reverse angle of negative 2 pi on 3, which is what we get when we subtract a full rotation off this 4 pi on 3 angle to put it back inside the proper domain. And if we observe the roots that we obtained before, we can see that is exactly what we got. We got this first value here of cos 0 plus I sine 0. Then the second root that we generated had an argument of positive 2 pi on 3 with a radius length of 1. And the third argument was one that had a negative 2 pi on 3 argument, so it went in an anti-clockwise direction with the same modulus. And this means exactly the same thing will happen if we consider taking these powers in exponential form, which brings into play our index laws, allowing us to multiply the arguments listed in those powers by a third. So this gives us a handy little method to use to be able to quickly solve these complex roots of unity equations, no matter what the power is. So basically, on the right-hand side, we want to rewrite this equation in polar or exponential form, list n number of that version of the value of 1 in polar or exponential form, and then take the nth root of every single one of those solutions that we've written on the right-hand side. Now, while it gets slightly trickier when we're working with an equation that is not a unit root value, we can apply the same method to a question like this one on the screen, where we're working with a basic polynomial equation with only the leading term and a constant that we can express in polar or exponential form. So the first thing we're going to do is rewrite this equation so that we have a constant value on the right-hand side that we can now express in polar or exponential form. So negative 64 is a real value that sits over here on the real axis. It means that it has a modulus length of 64, and this time it doesn't have an argument of 0 because 0 means that it hasn't been risen from positive x at all, whereas this root has made a full 180-degree turn to the negative side of the x-axis. So that means it has an argument of pi. So we can now list the negative 64 on the right-hand side of this equation in polar and exponential form. And then we know that we need to add lots of 2 pi, or a full revolution, 5 more times onto these values to generate the right number of roots. So we can see that that generates these 6 solutions here. So 64 cis pi, 64 cis 3 pi when you add 2 pi onto that already existing pi, then 5 pi, then 7 pi, and so on. And then we need to use on the left-hand side de Moivre's theorem to be able to divide each of those arguments by 6. And on the right-hand side, index laws to again be able to divide each of those arguments by 6. But because we're not working with a modulus of 1 here anymore, we're working with a modulus of 64, de Moivre's theorem also tells us that we need to take the nth root of that modulus as we take the nth root of z as well. So all of these 64s out the front will end up taking the sixth root of that value when we look to obtain z by itself. And the same thing in exponential form. As we raise that exponential form to the power of 1/6, we end up taking the sixth root of 64 to obtain each of our values, relevant values of z. And so as we adjust the domains of each of our answer, we can see that we get these 6 values here, and that they are conjugates of each other and evenly spacing themselves out around this Argand diagram. So we can see here that this gives us some general theory for when we're trying to solve either complex roots of unity or even just for the nth roots of a polynomial equation where we've only got the leading term and the constant value on the right hand side. So to do that, we're going to look to convert the right hand side of the equation to mod arg or exponential form first, because these are going to be the easiest ones to continuously generate multiple solutions in. We're then going to add 2k pi to the argument. So that means that we are going to add as many lots of 2 pi as we need to generate the right number of roots onto that right hand side. And then finally, to generate the roots, we're going to substitute the right values of k starting at 0, where we don't want to add any lots of 2 pi at all, and then 1 lot, 2 lot, 3 lots, and so on, up until 1 less than the number of roots we're trying to generate, remembering that the first root will be generated by adding no lots of 2 pi on at all. And we also saw before that if they use the notation of omega, then it means that we are working with those complex roots of unity. And so that means that the first root will be the real value of 1, and then omega as the second root, omega squared as the third root, and so on until omega to the power of n minus 1 to generate a total of n roots for omega, being roots of unity. So we can see in this example underneath how this sort of formula can help us to really quickly generate the right number of roots. And I know my writing is a little bit messy, but as you follow along, if they're asking us to generate the fourth roots of root 3 plus I, then they're asking us to create the equation where z to the power of 4, which will generate 4 roots for us, is equal to the complex number of root 3 plus I. So using these steps to solve, the first thing I want to do is convert the right-hand side to mod arg or polar form. So that's what I've done, and I end up with 2 cos pi on 6 plus I sine pi on 6. And then I want to add 2k pi onto that argument of pi on 6. And I need to do that 4 times, starting at a k value of 0, where I'm not adding any lots of 2 pi at all. And then 1 lot of 2 pi, 2 lots of 2 pi, and 3 lots of 2 pi to generate my 4 roots. Notice that I have also taken 2, the modulus, to the power of a quarter as well, and I've just written that in surd form too. Then, as my last step, I need to divide each of those roots by n, which in our case is 4, so that I am splitting it up into 4 equal parts around the Argand diagram and finding, rather than z to the power of 4, z by itself. And then the last step, just making sure that as I do that, each of my answers ends up within the right domain. So these last 2 here, I have subtracted 2 pi off the initial argument that I obtained to put them back inside the right domain as well. So again, it would be a good idea if you pause this video and write this final screen down as your theory notes in your book, and then we're going to explore some further examples, particularly some harder ones that they like to ask sometimes, particularly towards the end of your HSC paper when we're back in class.